Yeah, I came about 2 minutes late, because another faculty member was asking me about how to do screen recording. What kind of equipment do I use? What kind of program do I use? Can I do it in Windows? That sort of thing. So I was a little bit late because I just got stopped, on my way here. I think from here on I have to wear a ski mask when I move on campus, especially when I'm running short on time. I just wear a ski mask or a grocery bag with 2 holes on it. Huh? But they don't know who I am. I'll even have I'll even have a sign that says I am not tech, and with the underscore, under the not. I think that would work. All right. So this is an interesting. I think it's an interesting module in some ways, because this is the first time we actually deal with a memory device. So up to now, we talk about circuits. We talk about some fairly complicated circuits like a carry look ahead adder or borrow look ahead subtractor. The equation looks kind of really gnarly and have lots and lots of terms, but in some other way they're actually fairly simple, because everything only goes in one direction. Okay, there are no quote unquote loops. Okay, as far as the logic gates are concerned. In other words, we do not have a scenario where the output of one gate kind of indirectly goes back to the input of an earlier gate. We do not have that scenario up to now. So what we'll do is we are introducing memory devices now. A logic gate is not a memory device, okay, because the state of the output changes as soon as the input changes with a propagational delay. Okay, so it doesn't remember anything. Okay, if you change the input, the output changes accordingly. There's no such thing as memory when we talk about the AND gate, OR gate, and stuff like that. A memory device has a guarded internal state that remains unchanged until a specific input pattern triggers the change. So this is kind of an important sentence because it kind of qualifies what I count as a memory device. And up to now, we do not have anything that looks like this, where there's an internal state that remains exactly the same until a specific input pattern triggers the change, which implies there are other input conditions that would not change the internal state of certain types of designs. Okay? So the next thing we talk about is what we call an SR latch. So an SR latch is what we call a latch. It is not a flip-flop. It just latches on a particular state until the input becomes a certain thing. So what we'll do is we'll take a look at this somewhat pseudocode here. Okay, if you have taken cisp310, you really kind of should understand this kind of pseudocode. So NAND2, input pin, output pin, those are basically classes that represents, guess what? NAND2 gates. They represent input pins and output pins. Okay? And then circuit, because circuit is starting with a lowercase, it is not a class. Circuit, lowercase circuit, is representing the actual circuit that you're creating. The method add node, well, it adds a node. But in this case, a node does not mean the same thing as in 430 or 400. A node in this case is basically an electrical connection. So one node is one electrical connection, and then the parameters passed to the node constructor. Those are the things that we want to connect by that particular node. Okay? In other words, I am turning a picture into text here. So why would I want to do something like that? I mean, a picture is a lot more intuitive, so why would I introduce a way to turn a picture into text? What do you think? You can, well, right, exactly. It's easier to edit, okay? Because when you look at a circuit in a picture or pictorial format, if you need to make space for a new gate, that's a lot of work because you have to move a bunch of wires apart, you have to move the gates around to make enough space just to put that extra gate in it. But to do it this way, pretty easy. You just make a few new lines and make a few new objects and then make connections. That's it. But there's another reason. In industry, okay, how do you think Intel engineers design their new processors? Do you think they use LogicSim or something like LogicSim that is kind of graphical oriented? And why not? I see a bunch of people shaking their heads. Yes, go ahead. Yeah, go ahead.
I was going to say, because one, I did have experience with circuits in
Mm-hmm.
cisp310,
Mm-hmm.
and we did have the option of doing it through graphical design.
Uh-huh.
Normally said he wants us to specifically do it with coding,
Mm-hmm.
and it was more precise doing it through code. Like you can see what's occurring and what you're changing
Okay.
in code.
Well, that's one, but as I said, yeah, go ahead.
I feel like it's more organized to do larger scale like circuits through code.
Yep.
Whereas if you have it graphically, you have to like zoom in and be like,
Yep.
oh, what's happening, what's going on.
It certainly is more involved, to edit a picture, even though it is initially more intuitive, but as time goes on, it gets more and more and more difficult to maintain a design that is graphical instead of in text. But the other reason is actually quite simple. If you try to design a 64-bit adder that is using the carry look ahead mechanism, well, how long do you think that's going to take you? Quite a bit of time, right? But what if I say, oh, you can just use a loop to do it. In fact, all of the C++ control structure would work. Then how long would it take you? Shouldn't take a long time because I showed you the code already. Remember, I showed you guys the code, the C code that is corresponding to the equation for any carry bit in the carry log ahead mechanism. And there are programming, quote unquote, programming languages out there that can help you design circuits, and you can, quote unquote, script it. In other words, if there's a method, if there's a programmatical way to specify the circuit, what components connect to which other components, you can actually just write a code to do it. So I'll just give you a few pointers here because our main purpose of this class is not to talk about those topics. Yep.
Was that meant to be q.pin or q.pin?
We'll deal with that later. So one is called Verilog. Verilog is what we call a hardware description language. The idea is, we want to be able to describe a circuit using text and not a picture. Okay. So Verilog is used a lot in industry, and the other one is called VHDL. VHDL, which stands for VHSIC hardware description language. So those two are basically the most standardized languages out there, with Verilog leading by a long way. When you look at the syntax of Verilog, you would not be surprised. It looks just like C and C++. It's got loops, got conditional statements, got arrays and stuff like that. So some of you, may eventually end up using Verilog because if you are a computer engineering student or an electrical engineering student, you are very likely to have to use Verilog or VHDL to not only to design circuits, but also to design tester for your circuits. Okay? So these are interesting topics on its own, but I just want to introduce the concepts in this class so that you understand why I use a text representation, just to say, oh, okay. So the answer is correct. This Q comma should be a Q dot, okay, because it is a property of Q and it is not a comma here. So let me fix that, okay, because I hate to leave things that I know is incorrect unfixed. So let me just fix that here. And this one is in module 0298. And we're looking for Q, comma, pin. And there we have it. change it. Huh? Sorry?
And there is another one on
There's another one
the next line.
on the next line. This one?
No, it should be comma after the in.
Oh.
Bracket.
Oh, okay, I see. So one dot should be a comma and the other one should be the other way around. Thank you. There we go. And refresh. Oh. And here we have it fixed. Nice. So I kind of like to catch mistakes like that and make the fix right away, because if I try to remember, it's not going to happen. Okay, so what does this circuit look like? Well, we have two NAND gates, N1 and N2. We got two input pins, S and R, and then we got two output pins, Q and NQ. So let's try to do this in LogicSim. So we look at the text version, and then we'll implement this in LogicSim. Okay. And this is where LogicSim is. All right, so here's LogicSim. So we'll pull two NAND gates. Okay, we only have two inputs per NAND gate. And we can make these narrow like that. We got two input pins, two output pins, and then we also have two NAND gates like that. So let's try to start to label these things. So we got N1 and N2. This one is N1, and this one is N2. We got two input pins. One is S and one is R. And then we got two outputs. One is called Q, and the other one is called NQ. Okay, so we got all the ingredients. So with all the ingredients already done, we go back to the browser, and then we have four nodes. In other words, there are distinctly four electrical connections. One electrical connection goes from the S pin to one of the inputs, the first input pin of N1, the NAND gate. Okay, so that's pretty easy. Okay, so we switch back to LogicSim, and okay, I need to look at S pin. So I just try to make it look nice and align everything. There we go. Okay. The second one is the R pin. The R pin connects to the second input pin of N2, the other NAND 2 gate. So we'll go back to LogicSim and perform the same operation. Okay, so there we go. All right, so we got the two pins already set up, the first two nodes. Now the third and the fourth nodes are a little bit interesting, because as you can see, the output of N1, which is the output of the first NAND 2 gate, is connected to the first input of the second NAND gate. So this is where things start to go a little bit interesting. Okay, the output of one gate goes to the input of another gate, but it also goes to the output pin, one of the output pins. And then the second one is the second NAND gate output connects to the second input of the first NAND gate, but it also connects to one of the output pins. So let's go ahead and connect these pins one at a time. So we'll do the N1 first, where it accepts the output of the first NAND gate goes to one of the input of the second NAND gate, but it also goes to Q as an output. All right, so here's Q. This is the easy part. Okay, so this is a node already, but at the same time, this is the fun part that is missing from all of the other designs that we have up to this point. Is hey, it's kind of like a feedback. Okay, the output pin goes back to the input pin, and then the same thing over here. So this time we have NQ. And it also goes back to N1 in this case. There we go. Okay. So if you want to understand what a node is, okay, because the node concept is used a lot in circuit design, one thing you can do is to switch to the pointing tool or the poking tool. When you poke something and it becomes bold or thick, that is one single node, okay, which is representing one single electrical connection. This particular node so happens to connect 3 different points because it connects the output of N1, it connects the pin of Q, it also connects to the input, one of the inputs of N2. So that's the concept of a node, N-O-D-E, in electrical design. If you have taken, I think, one of the physics classes on electricity or electrical components, you will understand the concept of a node as well. But assuming that you have not taken that class, this is just a quick introduction of what a node is in that particular context. Do we have any questions about what a node is and how this particular design looks like? No questions? Okay. So if there are no questions, we'll look at this design, and in fact, we'll turn off simulation. Okay, so we go to simulation and disable and reset. Okay, so this way we do not get confused by the zeros and the ones, the dark green versus the light green and stuff like that. So we want to go through an analysis and say, well, what happens when S is 0? What happens when R is 0? What happens when both are zeros or both are ones? Okay, so we want to go through that analysis. When both S and R are zeros, do we know what's going to happen to Q and NQ? I'll let you guys kind of work on this one a little bit. And remember, these are NAND gates, which means they behave like an AND gate, except the output is negated. It is just like an AND gate, but with the output going through a inverter or a negation. Okay, so I'll let you guys kind of think about it. Is the pictorial version a little bit difficult to process? If that is the case, we can go for a text representation. So we'll go to a text representation and use a truth table. So truth tables can be very useful when it comes to the analysis of a circuit like this. So I'll put a truth table right next to it, so this way we can kind of evaluate it. Okay, so we got S and R, and then we have the negation of, well, let's just look at Q and NQ, okay? It's a little bit difficult to express the equation because of the feedback mechanism. So I'm just going to look at this, and we'll look at the easy one first, okay? What if S and R are both false, or 0, or low? What do you think is going to happen to Q and NQ? They'll both be true. Okay, very good. They'll both be true because, they'll both be true because with an AND gate, if at least one input is a 0, the output is going to be a 0. Make sense? But since these are NAND gates, which means the output is negated, if the output of an AND gate is a 0, the output of a NAND gate is going to be a 1. So it makes sense because N1 has at least one input being a 0, the output is guaranteed to be a 1. The same thing can be said about N2 because with N2, one of the input is guaranteed a 0 because the input pin is a 0, so the output is guaranteed to be a 1. Okay, any questions? Are we good on this? Yes? Mm-hmm.
How can you see what the output pin result is going to be when it's in a loop like that? Can you just make it fast?
Well, so the key is, with an NAND gate, if at least one input is a 0, the output is going to be a 1. So I don't even need to know what N2 is outputting, because just because the S pin is a 0, that already determines the output of N1. And then the same thing can be said about N2, because if we say R is 0, if that is a given, then N2 has no choice but to output a 1.
Okay.
Mm-hmm. All right. So are we ready for the next test case? So the next test case is, okay, let's say S remains to be a 0, R is now a 1. What is going to happen here? Well, one of them is guaranteed to be a 1. Which one is still guaranteed to be a 1? Q is still guaranteed to be a 1. What about NQ? What's going to happen to NQ now? Is it going to be a 0? Well, let's find out, right? Okay, R is a 1, so this is a 1. The other input of N2 is coming from the output of N1. N1 is guaranteed to output what? A 1. So we got 1 and 1 as the input of N2, and when you have all inputs of an AND gate being 1s, the output is going to be a 1. But this is a negated AND gate, which means if the original AND gate is going to output a 1, this one is going to output a 0. So NQ is going to be a 0 in this case. The other way around, I think that's going to be a pretty easy analysis because the design is symmetric. If you put a mirror horizontally, halfway through the design, other than the lettering or the labeling, they look exactly the same. So it is symmetric, vertically. Is that okay? So now the last remaining question is this. So the last one is, so far we haven't seen a memory device yet, right? It doesn't seem to remember anything. What if the input is 1, 1? Can you tell? Well, that depends on what was the previous state, okay? Was the previous one line 3, or is the previous state line 4? Is that making any sense? Okay, so let's check out those two, okay? So instead of doing this, we'll give you this scenario. I'll give you this scenario. So we have this state first. So this is the previous state, and now we transition to this state here. So this one, I'm telling you exactly where it came from, okay? In other words, all I did was I switched S from 0 to 1. What is that going to do? Is it going to do anything to Q? Okay, so let's analyze this a little bit, okay? So previously, okay, we have 0 going into S. We have 1 coming out of R, okay? And as a result, Q is 1 and NQ is a 0. So by changing the S pin from a 0 to a 1, would I have affected anything? I wouldn't have affected anything. I would not have affected anything because N2 is still outputting a 0. Because N2 is still outputting a 0, N1 would still be outputting a 1, and therefore not affecting Q. But because N1 is continuing to output a 1, and R is also a 1, that has not changed, so we have 1 and 1 going into N2, so N2 would still be outputting a 0. In other words, it maintains its previous state. Is that okay? So that's a separate scenario, okay? So the other scenario is this is where we were, okay? This is where we are. So in this case, what's going to happen to Q and NQ? Remember, the circuit is mirror image top bottom, okay? So what do you think is going to happen in this case? It's going to be the same, exactly. Oh, okay. So the input state of 1, 1, okay, using S is 1, R is 1, is really just saying, I'm just maintaining what I have. Okay? And therefore, we have our first kind of memory device, okay? It's not very useful as a memory device, but it serves as a very critical component for all other memory devices to come. Are we good so far? In a way, this is kind of like a NAND 2 gate in terms of how we build all of the other logic gates. It is the very basic component of all of the other devices. Then somebody is going to say, what if the input is 0 and 0, and then we switch to 1 and 1? What's going to happen? Because, hey, we talk about the 2. What about the third one? Well, let's find out, okay? This one is even more fun. So originally we have 0, 0, which guarantees 1, 1 as outputs, okay? That one is actually a very easy case to analyze. So now we say we are switching both inputs to 1 and 1. What is going to happen? Well, that gets a little bit tricky, right? Because N1, would suddenly realize and go like, oh, I now have both inputs being 1s. I want to switch my output to a 0. Yes? N2 is going to do the same thing. Now, if everything is done simultaneously with no propagational delay, then we have a really big problem, okay? But that is not going to happen. There's a propagational delay. In other words, to switch between line 16 and 17, it will take the gates N1 and N2 will both take a little bit of time before they change the output. So there's a little bit of time when they will maintain their outputs as 1 and 1. Is that okay? And that makes it possible for both of these gates, N1 and N2, to experience both inputs being 1s. It's not going to be a very long time. It's going to be measured in nanoseconds, okay? Probably a fraction of a nanosecond these days, okay? But it's going to be a very short amount of time, but definitely there is a certain length of time where the inputs of N1 and N2 will both be 1s. And after that amount of time, which is the propagational delay of a gate, both gates will now switch their outputs to 0s, right? So we now have 0 and 0 here. Okay? But then we have a problem. Because if both the outputs of N1 and N2 are both 0s, and they're going back to the other gate, don't you think we now have a little bit of a problem? Because now both gates, both N1 and N2, will now experience at least one input being a 0. Okay? And what do you think a NAND gate would do when at least one input is a 0? It wants to make the output a 1. But it's not going to do it right away because there's a propagational delay. So after a propagational delay, both outputs would become 1s. And then both outputs become 0s. And it will never end. In other words, we enter a state of oscillation. The circuit will now oscillate. And the half period of the oscillation is going to be the propagational delay of a gate. If the propagational delay of a gate is 2 nanoseconds, then the full cycle is going to be 4 nanoseconds. But every 2 nanoseconds, you will see a transition. Yep. Typically, we do not like that oscillation. But in principle, this is also how we build oscillators. So are we good so far? Yep.
So is it an example of a pin loop and just looping with no limit?
It is, in a way, it is a loop in the sense that, the states will transition, but eventually it will transition back to a state that was already seen earlier, and therefore it forms a cycle. But that cycle is not going to be, it won't stop until one of the inputs changes. Yep.
So is this basically how clock is made?
That I cannot tell, because I'm not a electrical engineer, so I cannot tell you whether, how clocks are done. I think this is not how they're done, because most clocks rely on a crystal to give it a very precise kind of timing. But crystals cannot run up to like 4 gigahertz where your processor runs. So what usually happens is there's an analog circuit to give you kind of like a base frequency, like maybe in the range of hundreds and hundreds of megahertz. And then there's a clock multiplier that is capable of changing a clock frequency to a much higher frequency. But I'm not a hardware engineer, so I can't really understand. I cannot answer that question with a very good answer. So are we good so far with what we call a SR latch? This is called SR latch. Can anyone guess what S and R mean? Okay, why do we call this a SR latch? Set and reset. Very good. Okay, so set is S and then reset is R. That's why the inputs are called, S and R. And then the output, Q is the actual output, and Q is actually just the negation of Q, or not Q. So typically, with a design like this, one of the output is not even, it's not going to be outside of the chip, because it's not really useful. But for the, from the perspective of discussion, they're both, useful. So are we good so far? Okay, let me test you one more time, okay? Why is this device the basis of memory devices? What makes it qualify as a quote-unquote memory device? What does it remember? Yes?
Well, because when you change one of the inputs, it will still have the same output.
Yes. Particularly when both inputs are ones, it remembers what it was before that state. Okay? Are we good so far? Okay? All right, so if we're good here, let me go back to Logisim, and I'm going to turn this into a circuit. So we'll turn it into a circuit and give it a name. So right now it's called main. I don't want to call this main. And instead, we'll call it SR latch, because that's what the name is supposed to be. And then we'll give it a label. Okay, we'll just call it SR. And I'm not going to label the input or the output, because it's pretty understood that SR, Q, and Q are kind of the usual way to label it. All right. So in the notes, we're going to move on. Okay. So you can read this part here, which is a clock by clock, or I would say transition by transition analysis of the state of the device itself. I just verbally described it. Okay, this is kind of like the formal representation of how the states transition as we change the inputs. And of course, we got this table. And it even talk about the oscillation. So if you read the notes, you'll get the same thing as what I just talked about, except it's just going to be written instead of spoken and with demonstration. So the next one is a little bit more complex. So now we have a D flip-flop. By the way, the D only stands for data. Okay, so it's not anything really interesting. Okay, so this is a data flip-flop. It has got one negation, one and NOT gate, 2 NAND gates, one SR latch, 2 input pins, one is D and one is EN, and 2 output pins, one is Q and one is NQ. So let's find those ingredients, throw it into the design, and then we'll hook up the nodes. Okay. So I'm going to go back here and make a new design. So I go to Project, Add Circuit. And this is called a D flip-flop. I just use a DFF for D flip-flop. All right, so I vaguely remember there's one SR latch that I need. In terms of logic gates, we need a single NOT gate. And then we need 2 NAND gates. Okay, so I pull this NAND gate, change it to a 2-input NAND gate, and then duplicate it. So now I think we got all the major ingredients. Let's double check. Oh, we got input pins and output pins too. Okay, so we need 2 input pins and then 2 output pins. All right. This is actually sometimes how people design products. They just get all the ingredients where they think, I think we'll need this, I think we'll need that, we'll need that. They put it into a box, and then they just shake it up, and here comes a new product. Huh? After you shake it. I need to update my BIOS. There's the cartoon of Dilberts. How many people read Dilberts? Okay, there are very few people. Okay, I guess it belongs to the older generation now. There's one Dilbert cartoon, where the pointy-haired boss, who's not very tech savvy, was using a laptop computer or tablet, and did not know how to reset or turn it off. So I think it was Wally. So Wally told the pointy-haired boss and say, just turn it upside down and shake, which was basically how you reset Etch and Sketch. And the pointy-haired boss could not differentiate between a Etch and Sketch versus a a computer. All right, so we got the negation gate, and I think the NAND gates are still called N1 and N2. So here's N1, and here's N2. The inputs are different from last time. One input is called enable, or EN. The other one is data, which is D. Okay. Oops. Did I? Oh, okay. That's not the right place. Okay, there we go. This is our D. Outputs are still labeled the same way. One is Q, and the other one is NQ. All right. So we got all the components labeled. The NAND gate and the SR latch are not labeled because they're pretty obvious of what they are. All right, so let's try to hook them up, okay? Draw wires between them. So the D pin, which is an input pin, goes to the first input pin of the first NAND gate. It also goes to a negation pin, NOT gate, which is kind of like a standalone thing, okay? So we'll hook up those three components. All right. And of course, I just forgot where. Yep, there we go. So we got the D pin, so the EN goes down, D pin goes up. There we go. There you go. Okay, so it goes to one of these, and then we have the NOT gate here, and then the D pin hooks up to the only input of the NOT gate, like so. So that's one node. So let's look at the second node. The second node says we want to hook up the EN pin to the other input pin of N1 and the first input pin of N2. So it hooks up to both of the NAND gates, except hooks up to the second one of the first one and the first one of the second one. Okay. So we'll have it perhaps here. Okay. And EN goes to the first of the second gate, but at the same time it goes to the second of the first gate, like so. Okay. Now we have to look at the output of the negation. It goes to the second pin of the second gate. All right, so we need to move this guy down a little bit, and to make it look nicer, okay, we can do that. All right. What else? We got the output of the first NAND gate going to the S pin of the SR latch. So this is the S pin. So we got this picture going like this. I realized that I missed two lines in the design, and I'll show you what I mean by that. Because we are done following the instructions here, and you can see how the output pins are not connected. They're floating. So what do you think we should do about the output pins? The Q of the SR latch goes to the Q pin, and then the NQ of the SR latch goes to the NQ of the pins, okay? All right. Because these are really just to externalize the output of the SR latch, just so that we can see, what it does, okay? And of course, I will make changes to the notes right away, just so that it is up to date. Okay, so go back to the notes. And go back to the first terminal. And of course, I cannot remember which one it is. 8, okay. We need to look for D flip-flop. There we go. Okay, so what we are hooking up is the SR latch Q pin goes to Q dot pin, and then the SR latch's NQ pin goes to NQ's pin, and that's it. Okay, go back to the design, refresh, and now we got the whole picture. Oops. Scroll down, scroll. There we go. Okay, so we got the whole design now. So now the question is, how do we analyze this whole thing? Well, let's take a look. What happens when En is a 0? Now, look at how En is connected. Okay, so let me just click on it. I'll use the poke tool to click on the output of En. And now you can see where it goes, right? It goes to both of the NAND 2 gates, which means both of the NAND 2 gates will have an output of 1, right? Exactly. Okay, so can someone remind me again what happens when both inputs of an SR latch are 1s? Maintain state, do not do anything, right? Okay, so that means when En is a 0, nothing can happen to the SR latch. You can flip the data pin as much as you want, but nothing is going to happen to the SR latch. Whatever it was, it will maintain. Is that good so far? That's why it's called an EN, or enable pin, because when the enable pin is a 0, it means the whole circuit is quote-unquote disabled. When it is disabled, then nothing will happen to the SR latch, no matter what you do with the data pin. Is that okay? Are we good so far? What if I make the EN pin a 1? What's going to happen? So when you put a 1 into the EN pin, that becomes a 1 going to both N1 and N2. One of the input is a 1 guaranteed, which means whatever pin is left is going to determine the output of the NAND 2 gates. Does that make sense? So what is the remaining pin of both of these NAND 2 gates? One is receiving the data pin non-negated. The other one is receiving the data pin negated, right? So let's say that the data pin is a 0 and the EN pin is a 1, okay? I'm even going to go through that scenario, okay? We put a 1 here and the data pin is now a 0. What do you think is going to happen to the latches, to the SR latch? Okay, so the EN pin is a 1 going into N1, but the data pin is still a 0. So that means N1 is going to do what? N1 is going to output a 1. Okay. What about N2? So both inputs of N2 would be 1s because the data pin is inverted before getting into the input of N2. So N2 would experience both inputs being 1s, which means it's going to output a 0 instead. That 0 is going to SR, it's going to the R pin, okay, which means it's going to reset the SR latch, and as a result, the Q is going to be a 0. Is that okay? What if it's the other way around? What if we are looking at this particular scenario? What if I change the data pin to a 1, while the EM pin is also a 1? Well, in this case, N1 will have both inputs being 1s, which means the output is going to be a 0. The output of N1 is going to the S pin of the SR latch, which means it's going to set the SR latch, which means Q is going to become a 1, and Q is going to be a 0. Is that okay? So to summarize, okay, when the EM pin is a 1, the state of the D pin as an input pin is going to be mirrored by the Q pin of the SR latch. But when the EM pin is a 0, then it will just remember whatever the SR pin, whatever the SR latch is, and the data pin is not going to change a single thing. Okay, so talking is difficult to explain it, so let's go ahead and visually see what's going to happen. So we go to simulate, turn it on, and the first thing is I'm going to disable the enable pin first, and then keep flipping the data pin, see nothing happens to the output of the entire device. Are we good so far? And then we go ahead and turn on the enable pin, and you can now see however I change the data pin, the Q pin is going to mirror. I can turn it back to a 0. The Q pin is also going to turn back to a 0. So is this looking more like a memory device now? You have one pin that says, don't pay attention to me, and then, the other pin is going to say the message. So if the enable pin is a 1, that means, hey, memory device, pay attention to me. Remember what I just said. And then the Q is basically the memory. But if the EM pin is a 0, then you're telling the device, don't overwrite your memory, okay? Keep whatever you are currently remembering and don't change the state. Then no matter what you do with the D pin, as long as the EM pin is a 0, the device will still, quote unquote, remember its previous state. Yep. No, it's enable. It really is just enable. It's really it's telling the device whether the device output should mirror the data input pin or not. That's what the EM pin is saying. So when the EM pin is a 0, no matter what you do with the data pin, the Q pin maintains its state. When the EM pin is a 1, then whatever the D pin is, the Q pin will follow. Are we good so far with a D flip-flop? Okay? All right. So if the D flip-flop is okay, we'll switch to the notes here. And we talk about what we call an edge-sensitive D flip-flop. So edge-sensitive D flip-flop is a little bit more complicated. So you can see that these designs actually get more and more complicated. This one is particularly interesting because it has got a 3-input NAND gate, which is the first time we use a 3-input NAND gate in anything in this class. Okay, so let's go ahead and make this one too. Okay, so we'll go ahead and create this design. And what I'll do is I'm going to put it side by side here because otherwise I have to flip-flop between the two screens a lot. So we'll add another circuit here. And this one is called a edge-sensitive D flip-flop. It has got 2 SR latches. So the SR latch is now becoming a component of all of the higher level designs. So we go to SR latch and say, yep, we need 2 of these. And we'll name them because they need names. One is C and one is S. Okay. You can actually tell how Logisim is in a way object-oriented because when we click on SR latch over there, it's actually kind of like a class. Every time you click on SR latch and bring the design to the circuit side, you are instantiating an object. Do you guys kind of see that resemblance with your object-oriented programming class? And then each component has its own name so that we can refer to it, just like a variable of a certain class has its own name so that we can refer to it. All right, we need two NAND gates. One is 3 input, the other one is only 2 input. So we go to gates, and then we pull 2 NAND gates. Okay, one only has 3 inputs. And then the other one has 2 inputs. The one with 3 inputs is labeled N1, and then the other one is labeled N2. All right, we got 2 input pins again, but the input pins are no longer labeled the same way. This one we can still call it D or data. Okay, doesn't matter. Okay, but the other one is not enabled anymore. The other one now has a name of clock, C-L-K. Okay, so that's kind of new, different from before. And then we have one single output pin, which is Q. There we go. And I think we got all the ingredients done at this point. So now it's time to actually just do the hookup or wire up the whole thing. I just want the design to look kind of nice. So let's see. Okay, clock pin. Yeah. All right, so nope. It's supposed to go to the second one. I want to maintain the order as well. Okay, so that takes care of the first connection, going from the data pin to the second input of N2, the NAND gate. This one is going from the clock pin to the R of the SR latch and also going to the second input of the NAND gate here. Okay, so we'll have this NAND gate here, and this one goes to the second one like that. But it is also supposed to go to the R pin of the SR latch. So let me see how to make it look nicer. Okay. Like so. All right, so that takes care of the third line. Let me see. Yeah. No, this is taking care of the second line. So we're now moving on to the third line, which takes the output of N2, bring it to the last input of N1. Okay. I may not have left enough room, but we'll see. So that takes care of this one. It also goes to the S pin of the SSR latch. So that's kind of handy because it's right here. Okay. We're moving on to the fourth line. The fourth line takes N1's output and bring it to the first input of N2. Okay. So we'll do a loop around here like that. It's also going to the R pin of the CSR latch. So the R pin of the CSR latch is the one at the bottom. So we bring it here. So that takes care of the fourth node. Now we're moving on to the fifth node. The fifth node takes the NQ of S, which is this one here, and bring it to the first input pin of N1. Okay, this is going to look ugly. Yeah, we can tunnel. But let me see if I can make it still look reasonably pleasant. I used to do a circuit design, so I can do that. All right, so, and it also goes to CS, okay? So C.S is here. Okay, so S.NQ go to C.S. Yeah, we got space to do that. There we go. And the last one is to take the Q output of the CSR latch, which is this guy, to the Q output pin, and we are done. It has a little error here because, remember, we have problems when both input pins are ones. There's no previous state to remember. So this particular SR latch is going like, well, you're asking me to maintain the current state, but I do not have a current state to maintain. So that's why it's not happy about it. Okay. So the analysis of this circuit is a little bit more complex. Okay, if you go through the analysis part here, it's actually quite a bit more involved. Okay, so instead of going through all that, I'm going to let you guys read about it and try to understand it. Okay, I can make this Logisim circuit file available to everybody, so this way you don't have to reconstruct the circuits, so you can use it to help understand how the circuits work. Okay? But what is the bottom line? I mean, this design looks kind of overly complicated, so what does it do? So let's go ahead and describe it. Let me describe it. So the clock is basically, I'm turning the design from level sensitive to edge sensitive. Okay, so the first concept that we have to understand is what is level sensitive, versus what is edge sensitive. Level sensitive means as long as the enable pin is a 1, whatever the D pin is, the Q pin is going to follow. Is that okay? That's what we call level sensitive. It's kind of like an old-fashioned mic, okay, where there's a button that you can click on, right? So if you want to talk like a walkie-talkie, as long as you hold that button down, whatever you say is going to come out from the other side. Is that okay? That's level sensitive. You press the button to talk, but as long as you press the button, you can continue to talk. Okay? Are we good so far? Now, edge sensitive is a little bit harder to describe. So let me find a trap. Okay? Mousetrap is an edge sensitive device. Okay? So when you think about the mousetrap, okay, first of all, let me make sure everybody knows what a mousetrap is. And I'm not talking about the fancy electronic ones. I'm talking about the really old style, really inhumane type of mousetrap. So do we understand what a mousetrap is? Big, huge spring with a trigger. You put a little piece of cheese, somewhere, right? Okay, Michael is squinting. But do we know what it is? Okay, so let's take a look at it. Hopefully the first image that I pull up is not a inappropriate image because of gore. Okay, that's not too bad. So we can look at a mousetrap that has nothing in it. Okay, mousetrap, pretty simple device. It has got states, right? It has got 2 states to be exact. So is the trap triggered or not? That's basically the two states. Which side is this main clamp thing? Is it on this side or is it on the other side? That's the state. Okay? But what makes it change the state? It's not level sensitive. It is edge sensitive. So which edge are we talking about? That's the edge. Okay? So when this lever goes from this state to this state here, it will let go of this particular point, okay? So now let's see, I have to understand how a mousetrap works, right?
The long piece in the middle goes back.
Yeah, so the other side, there's something we cannot see on the other side. So basically this will flip this way, and so the main spring will take this wire and flip it all the way to the other side. So it's an edge-sensitive device. It will only change the state when this event happens. Is that okay? Now, it will only change the state well, this is not really a very good example because it can only go in one single direction, where a D flip-flop can go in both directions. So, but the idea of using this picture is just to understand what is level sensitive versus what is edge sensitive. Okay? Are we still good with what is edge sensitive? Okay. So we go back to Logisim, and this time we actually show the edge sensitive aspect of this particular flip-flop. Okay, I can do this all day long. You can see nothing happens, right? So now the data is a 1, okay? As soon as we have a rising edge on the clock, the output changes. Is that okay? But after the clock is a 1, now it's no longer changing. I can once again do this all day long, and nothing happens to the output. I can change the data back to 0. You can see the output doesn't change. Now, the edge sensitivity does not go in both directions. It is only rising edge that is sensitive. In other words, it's only at the very moment of the clock changing from 0 to 1 that whatever D is will be copied to Q. Okay? So a falling edge doesn't do a single thing. Yes?
That's why it's called a positive edge.
That's why it's called a positive edge sensitive D flip-flop. So I can now create a falling edge. Okay? If the clock is going from 1 back to a 0. See how nothing happens to the output pin? I mean, internal to the circuit, you can see some wires changing color, but the output pin doesn't change. But if I were to change the clock again from 0 to 1, the output changes. So this is why we call it a positive or rising edge sensitive D flip-flop. Okay? So let's stop for a moment, okay, and make sure that we all understand not necessarily the step-by-step of how it works, but as a box. Okay? If you look at an edge-sensitive D flip-flop as a box, do we understand the behavior of the box? Not necessarily all the gearing and whatnot is inside, but if we just look at the outside of the box, do we understand what it is? And how it is different from a normal D flip-flop, which is level sensitive. So are we good? Yes? Yes, go ahead.
Is it like a clutch? Then cars move?
No, it is not, because a clutch really is a level sensitive thing, because as long as the clutch is released, your drive axle is connected to the gearing, which is now connected to the drive axle. So it is not. So that is not an edge sensitive example in real life. Traps are definitely mostly edge sensitive. You step on it, which is the motion of the trigger going in this direction, and then the device actuates and changes the state. But it cannot change the other way. So we don't really have a whole lot of real life examples that is both edge sensitive and can change the state in both directions. So are we good so far with the behavior of an edge sensitive D flip-flop? It's good? Yep.
What's the use of the data pin?
Well, the data pin still dictates how you want to change the output. So if I want the output to become a 1, I got two things to do now. First, I have to change the data pin to a 1, And then the second thing is to create an up rising edge, which means the clock has to first reset back to 0, and now go to 1. Then the output is now mirrored. Yep. So the data pin is still, if you look at this as a copier, okay? If you look at this as a copier, the original is where you put what you put on the data pin. And then whatever is at Q is the Xerox. That's the output, that's the copy of it, okay? So clock is now, it's controlling whether it's edge sensitive or level sensitive. This is more like a camera, okay? Okay, this is a good one. A camera versus a camcorder, okay? This is a camera, okay? It takes a picture, okay, or it takes a snapshot. When you press the shutter release, the motion of pressing it down creates the edge, okay? And that edge is causing the mechanism to capture right at that moment what is the input or the lens of the camera to the sensor, which is then captured as an image, okay? When you release the shutter release, nothing happens because it's only sensitive in one single direction. Does it make sense? Okay, so that's a very good example. I should use it next year. Maybe I should write my notes right now and just say, this is like a camera, whereas the other one is more like a camcorder. Why do you think the other one is more like a camcorder? As long as you keep pressing the button, okay, this is an old style camera, right? Old style camcorder. So as long as you keep pressing the button, it will continue to capture the input to the output, which is what a camcorder does. Is that okay? More or less? Okay. So I think we are ready for the next device. So I'm losing track of all my tabs here. So let me consult my tabs outliner. This is how I can keep track, or hopefully keep track of all my windows. There we go. All right. So the next one is what we call a clocked and gated D flip-flop. So with this one, I gave up on using the text representation because there are just too many wiring and I just did not want to deal with it, okay? So this one, when you look at the input, now we have three inputs, okay? And the 3 inputs goes like, well, we know what data is, okay? Data is where you put the original on the Xerox machine, okay? We got that. From the first design, which is level sensitive, we know what EN does, right? If EN is a 0, nothing happens. When EN is a 1, then we start to mirror the input to the output. But this one also has a clock input, which means, hey, the clock means it is edge sensitive, okay? Nothing happens except for the moment when the clock goes from 0 to 1. But this has got both the enable and the clock. So what is the deal here? What do you think? So if the enable is off, if enable is a 0, you can clock all day long. Nothing happens, okay? At the same time, if the enable is on, but you do not have a rising edge clock, also nothing happens. So in order for something to happen, in order for the state of the data pin to be mirrored to the Q output pin, 2 things need to happen. Enable should be a 1. And at the same time, there has to be a rising edge. Both needs to happen in order to capture the input, which is on the data pin, to the output pin Q. So what is an example of this particular design? It's a camera, because it's a one-shot thing. It is a camera. But it's a camera with a safety, like a gun. So in addition to the shutter release, there's a safety. You can call it an on-off switch, okay? So if your camera is off, you can keep pressing that shutter release, nothing's gonna happen, right? You can turn on the camera. If you don't press the shutter release, nothing is gonna happen. It's like that, okay? So if you cannot write down anything, if you cannot remember anything, just remember this is like a camera. Yes, digital camera. Yes.
So why is it called clock? Is it something to do with time?
Huh?
Why is the clock pin called a clock?
It is called clock because it is usually hooked up to the clock, the system-wide clock of a design. Yep.
Isn't it clock like an alternating
Yes. So the clock line or the clock pin is usually connected to what we call a system clock, and the system clock does a very boring thing. What do you think that is? It oscillates between on and off and on and off and on and off and on and off for eternity at the same frequency. So it's not like, it can even change the tone. It's the same tone all the time. Okay? But what it does do is it is like a metronome. It establishes timing. Click, tock, tick, tock, tick, tock, tick, tock. Okay? Why is timing important? So that becomes the next question. Yep.
You want to be able to make sure that you're getting the right part of the signal at the right time.
Exactly. So timing is important because you want to make sure that when this thing is ready to accept an input, that thing is ready to output. So that's why you need to match the timing. Okay? Is that okay? Yep.
So as more we have SRs, then the more time we need to, so they process the data, right?
There's more propagational delay, yes. But in terms of the propagational delay versus the period of the time, we're still talking about a pretty good order of magnitude. So if the propagational delay is, let's say, 2 nanoseconds, then we are talking about at least a microsecond in terms of the clock timing. So we are still pretty safe. We're not going to run it close to the edge. Is that okay? So with this picture, remember this is like a digital camera. Okay? If you want to take a picture, remember two things. Turn on the camera first. That's your enable. And then press the shutter release. That's your clock. Okay? If you do not do one of those two things, nothing happens. Yes?
So in practical applications, the clock is just always going, and so whenever you have enable on and you're changing the data bit, you just have to wait that one nanosecond till the next rising edge automatically happens, or is there or is it visually controlled?
Okay. So let me explain the importance of each of these pins. Okay? I think the data pin is not going to be a very important one to explain, because that's just the input, what you potentially want to remember. And then the Q pin is also not going to be very important. That's just the output or the state that you have just remembered. The enable pin is basically saying, should you be paying attention? Okay? Now, why is that a big deal? Because now I can tell you, many components inside a processor, their data pins are all interconnected. They're all connected to the same thing. It's a multi-drop type of environment, just like in a classroom. Okay? When I talk, all of you can receive that signal all at the same time. It's a multi-drop application. So, but inside the processor, not every single device need to take note all at the same time. They don't want to pay attention to the same thing all at the same time. Okay? They need to pay attention to particular devices. So sometimes you don't want a device to take notes. You don't want a device to be active. So you basically say, okay, device XYZ, okay, I want your enable to be 0 because I don't want you to remember anything. I'm not talking to you, okay? The timing is important because when two devices are communicating with each other, you need to make sure that when the second device is ready to accept the input, the first device has the valid output already. So that's controlling the timing. Okay, so one more image that you can take away from today's class. If this is an instrument in an orchestra, the clock pin is controlling the tempo. Okay, 1, 2, 3, 1, 2, 3, 4, 1, 2, 3, 4. It establishes the timing. Think about, when was the last time you went to a middle school band rehearsal? If you have not been to one lately, go to one, okay? Because that will tell you what happens when there's no clock, or the clock is skewed, or the devices do not pay attention to the clock, okay? That's what the clock is for, okay? Synchronization. What about the enable? The enable is the conductor saying, shh, shh, shh. Flutes, cut off, and bring up the clarinet or something like that. When a device does not pay attention, or when the musician does not pay attention, what happens? All you can hear are the trumpets. Where are the flutes? No flutes. So enable is the volume control of the instrument, and then the clock establishes the beat. Okay, so that's kind of what we're talking about here. There are no new labs, so tonight we're just going to be continuing to work on the positive exponent homework assignment. So if you haven't done already, there are no new activities for the lab. Let me turn off the mic first.